answers to Friday's work is up on the screen. A mistake has been found by Matthew or Muller. Muller found a mistake. Evelyn, I see that hand. Very non-committal hand. Yes. Yes. Why? The periodic tables that I've given you will contain the most common ion charges, just because it doesn't, especially for the multivalent ones, just because it doesn't include a possible Roman numeral on the table doesn't mean that you can't make it happen if you need to. So if they give you a Roman numeral that isn't found on the table, use the Roman numeral anyway, because the table only includes the most common, not all of them necessarily. Yes. No. You did not, did you? Well, then you did way more bonus extra practice than you needed to. And I thank you for the extra effort. I apologize. I did, I guess on your guys, did I not? That's block C's. Where's block D's? You guys are block D. I wrote it on your guys' homework at the bottom, no balancing. So any of you who did the extra bonus balancing, so proud of you, it was unnecessary. And in fact, went against the instructions that I gave you. But hey, so you did extra work. I love it. Then there was a worksheet I gave you. Looked like this. Here's questions 1 through 6. One of the things I did tell you is if I give you the common name of something, Google it. So questions 5, 6, and 7 all included acid names. I have not taught you how to name acids. I will not teach you how to name acids. It's no longer part of the science curriculum. If I tell you you needed hydrochloric acid, it's actually, I didn't tell you this, but on the back of your formula sheet or your periodic table, it's there. But you could have just easily Googled hydrochloric acid and Google would have told you HCl. Phosphoric is H3PO4. And sulfuric from number 7 is H2SO4. Aha, there you are, stupid thing. That phone can... Ah, I love it. Now you're listening to me. Now you're not listening to me. I hate you. Come on. Ah, boom. And there's the last one. Last two, rather. Comments, questions, concerns on anything I have given you for homework. Evelyn, did you balance all of everything? Did you balance this worksheet too? You only balanced this worksheet. Oh. Okay. Because I don't have the answer key for these ones balanced, but I have the answer key for the other ones balanced. If you balance the other ones, I can show you those. But if you... Okay. Okay, so is there anything anyone would like me to go over? Muller, have you caught any more mistakes? Or was it just the one? You think I'm good? Okay. And then today's lesson is short. The practice is long. And it will lead into the lab that we are going to do tomorrow. Tomorrow's lab needs to get split over a couple days because we do need fire for one part of it. But we'll be doing the lab in the classroom. Obviously, I don't have fire in my room, so. Okay, here we go. Find me, not that page. Where's your book? You guys are block this one. Find me this page. Chemical reaction descriptions. Let's go back to you. Sahib's away. I just saw Sahib in his math class last block. Shame, Sahib. Shame. Okay, so we started with skeleton equations and balanced them. Friday, we looked at word equations to skeleton. I told you didn't have to balance. Today, we're going to bring back the balancing because you got lots of time. And we're going to look at chemical reaction descriptions because this is how you're going to be presented to them in labs. If I showed you a YouTube video, this is how it would show up. As you guys are watching stuff happen, either the description will be given to you verbally, like I will tell you what it is, or it'll be given to you written, and it will be your job to then go ahead and say, okay, what's actually going on here? What's being produced and in what ratios? And so this is kind of what's going to put it all together and what I'm going to get you guys to do in your lab tomorrow. So sometimes you're going to be given a sentence or a paragraph description of a chemical reaction and asked to create balanced equations. The steps we've all done already, we're just going to start putting them all together. The first thing you're going to need to do is you're going to need to turn whatever I give you into a word equation description. And this just involves taking out, it's like a word problem in math. What are the important bits? What can I actually ignore? What extra bonus junk is the teacher trying to just throw in here to screw me up? Pull out only what's important. Once you've pulled that out, turn each compound, whether it's ionic or covalent or a common name for something, or if I give you just an individual element, that's what goes there, compound or element, whatever those names are, now you have to turn them into a chemical formula. So you're looking for diatomics. You're looking for polyatomics. You're looking for covalent compounds. You're trying to see if I've thrown you a common name that you now need to Google. Like, what's the chemical formula for water? I don't know. Do we Google these things? On a test or a quiz, if I give you a common name, I will fully expect you to throw your hand in the air and say, what's the formula for such and such? And I will either tell you, well, good thing you asked. It's this, or I will say, I'm not going to tell you. In which case, if I tell you I'm not telling you, that's your clue to start digging through your periodic table and polyatomic ion chart, because it'll be there somewhere. Okay. Then it's exactly what we did on Friday. It's setting up your skeleton equation and balancing it. I will demonstrate for you, I'll give you 2 examples, and then I'm going to free you to practice this stuff while I'm going to go and start setting up your guys' lab for tomorrow. Start bringing chemicals and stuff into the room here. So here we go. First example. A piece of metallic zinc is placed. That's, if you didn't fix it last week, you should have fixed pulsed to placed. Is placed in a blue solution of copper 2 sulfate. A reddish brown layer of metallic copper forms in a clear solution of zinc sulfate. Okay, first thing you've got to do. Let us separate out the reactants and the products and get rid of all of the things that don't matter. What is coming together to react in this reaction description? What are the only pieces that matter? Muller. And? No. Yeah, you need this whole piece. The copper 2 sulfate. Does it matter that the zinc is metallic? Does it matter that the copper 2 sulfate is blue? No. At this stage with what you're doing, it doesn't matter. When you're actually in the lab, these things will help. If I just told you grab the zinc and the copper 2 sulfate, there's going to be 1, 2, 3, 4, 5, 6, 7 bottles of things that you're going to work with tomorrow. If I said get the copper 2 sulfate, or I said get the blue one of those is going to be easier for you to do. If I ask you to get the blue one, you find the blue bottle. If I ask you to find the copper 2 sulfate, yes, then at that point you're now reading labels on every jar. So there are cases where it's important to know the solution is blue, but not for a skeleton equation. Once you've actually found the things, I don't care what color it is, I don't care what state it's in, just condense the pieces that you need down into the word equation first, and then the skeleton equation. So we're going to be working with zinc. We're combining it with copper 2 sulfate. Nothing else about the reactants matters. There's a Metallica song in there somewhere. Nothing else matters. What happens afterwards? Well, it says a reddish-brown layer of metallic copper forms in a clear solution of zinc. So these two have clearly reacted. I've thrown down my arrow. What are the products? Someone said zinc sulfate. That's the clear solution. At least that's what it says in the description. What else has formed? Someone said it over here, louder. The copper. It's like the example I gave you on Friday, the distracted boyfriend meme. Zinc's walking by, copper 2 sulfate's walking the other way. Sulfate sees the zinc and goes, ooh, and now copper's on its own. So we've got our word equation. Now we need to go ahead and, how this happens is irrelevant. It just does at this stage. Now we need to go ahead and we need to make our skeleton equation. When you're making your skeleton equation, we're always going to, and we can frame it right below the word equation. We're going to put a line to represent the coefficient that we're going to use to balance these things, because today you're going to be balancing. The plus signs are going to show up. The arrow can be where it was. We've got our framework now for the skeleton equation, and we can just fill it in. What's the formula for zinc? Louder, Romina. It's just going to be, and Evelyn, thank you, same time. It's just going to be Zn. Zinc, when a metal shows up, it shows up alone. It shows up as an atom, so it's not charged. It's just Zn. So I got my space. I got Zn plus. Now I got to make copper 2 sulfate. So that's a compound, so we have to build the compound using our compound building rules. So this thing's ionic because it's copper and sulfate. This thing ends in ATE, so it's one of the polyatomic ions. So let's go ahead and build this thing properly. Copper is Cu. What's the charge on the copper ion? +2. How do you know, Evelyn? Because it's got the Roman numeral. Use the Roman numeral as written. Even if the Roman numeral doesn't line up with what you see on the table, use the Roman numeral. And now we've got sulfate. It ends in ATE, so you'd go ahead and you say, okay, well, ATE, polyatomic ion. Where the heck is my polyatomic ion chart? Here it is. 8 is SO4. Charge of -2. So then, what is the formula going to be then for copper 2 sulfate? Sorry, Matthew, louder. It'll be CuSO4. You betcha. The charges are equal and opposite, so I only need one of each. Or you could swap, drop, reduce. And now let's go build our products. The easy product to build is copper, just on its own. So the formula for copper is Cu. Zinc sulfate. Zn, what's the charge on zinc? Is he right, Brooklyn? You betcha. He is. Zinc +2. Sulfate, we've already looked up, SO4 -2. The charges are equal, the charges are opposite, so building this thing is easy. It's just going to be ZnSO4. And now we can go through the exercise of balancing this thing. Drop the line. Zn, Cu, S, and O. Zn, Cu, S, and O. I've got how many zincs on the left? How many coppers on the left? How many sulfurs on the left? How many oxygens? How many zincs on the right? How many coppers on the right? How many sulfurs on the right? How many oxygens on the right? So the beauty of this chemical reaction is it's balanced. There's no more work to do. We are done. 1, 1, 1, 1. C'est fini. Questions, comments, concerns about what I've done? Okay, we're gonna do one more. When you're ready, flip the page. We're gonna do number 6. Matthew, you got a 5 flip? You were just writing. Are you good? Okay. Here we go. We're gonna do number 6. You got to be careful with how you put these things together. Descriptions are going to show up a bunch of different ways. So here we go. Question like 6. When heated, solid aluminum oxide breaks down to produce aluminum metal and oxygen gas. There's your sentence. Let's build the word equation. What are the reactants? Or I'll do it this way. What are the key words that you're looking for to separate reactants into products? Evelyn. Which question are you answering? The first question or the second question? I asked 2 questions because I fixed. Okay. My first question was, what are the reactants? Is that your answer to that question? Yeah. You are correct. Are there any other reactants? What is the, so now this is where my second question is going to come back. Where or what key word or words differentiates or separates the reactants from the products? To produce. As soon as you see to produce, everything to the left are reactants, and anything to the right is a product. To produce is the arrow. So are there any other reactants? Are there any other reactants? Evelyn said aluminum oxide is a reactant. She is correct. Are there any more things left of to produce? The only other thing there that could conceivably be considered as part of the reactants is, as Romina just said, heat. Is heat something we can give a chemical formula to? What would be the chemical formula for heat, Evelyn? But can we give a chemical formula with things off the table for it? So you are you both said opposite things, but both of you are absolutely right. So Romina, my first question was, can you write a chemical formula for heat? You said no. You're right, you can't. Evelyn, you said, well, it's debatable because if it shows up on that side, we could talk about how we're putting like plus energy into the left-hand side on the reactants, and we will get there. We will do that. At the very last topic we're going to talk about in chemistry in Science 10 is whether a reaction is what's called exothermic or endothermic. And that is, where does energy show up in the chemical equation? At this stage, we're not going to add it. Like, I wouldn't put plus heat as a reactant. It's not like I can go to my jars of chemicals and say, I'm going to get heat jar. Can't do that. So because I can't do that, there's no chemical formula for it. On a word equation, I wouldn't necessarily include it. But we are at the very last thing we're going to look at exothermic versus endothermic, and when we do, that's where heat's going to show up here. So technically, unfortunately, both of you are correct, which makes it kind of confusing. All of that to say we're not going to add it yet. Not necessarily. So I'll tell you, because we're going to do this. No, we're going to do this. You're not actually melting anything here, believe it or not. Aluminum doesn't necessarily melt. when it's heated. You can force it to release the oxygen gas, but it doesn't necessarily turn to molten aluminum. That would be a pretty wild amount of heat. More than I would ever consider safe in the lab. So aluminum oxide, when heated. Heat at this stage, there's no formula for. Don't include it. So because there's no formula for heat, we're not including it at this stage. There's nothing else to list as a reactant. Aluminum oxide is the only one. When aluminum oxide is heated, what are the products? There are two of them. Aluminum and oxygen. One of the things that showed up in my C block class is that they argued that there was in fact two reactants, aluminum and oxide, those things being separate. What you need to remember is that when something it ends in IDE, it's part of this compound. It's not aluminum and oxygen that are reacting, it's aluminum oxide and oxygen that are being produced. There is only one reactant, there's two products. Cool, so now I can go ahead and I can build these things. The easy one to do are the two on the right-hand side. So I'm gonna put a that, I'm gonna put a that, I'm gonna put a this. I'm gonna build the framework for my skeleton equation that I'll then go ahead and balance. Start with the easiest thing. The easiest thing to list out of my three options is what? Which formula? Oxygen. Oxygen is what? Is it O or is it O2? It's O2. It's one of the 7 diatomic elements. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Nobody knows about anything below that. Because AT, and it's not on that table, but it's on this table, AT and TS don't exist long enough for us to know how they behave. I actually saw a really interesting video over the weekend. It just showed up on my feed. Maybe my phone listens to me while I teach. It showed up on my feed. We don't, like AT is below I. We don't actually know what astatine does because it doesn't exist. It is the rarest naturally occurring element on our planet, and it only exists for like a fraction of a second before it breaks down into other stuff. So we don't actually know how, we have no idea how it behaves. If you took all of the astatine that's currently on our planet and put it together, it would fill a single shot glass. That's it. There's about 2 ounces of astatine at any one time on our planet. Whole Earth, about this much. How do you, sorry? It's part of various so there's a process called radioactive, there's a few processes and they're all lumped into a process called radioactive decay. And anything that's radioactive decays. And so it shows up, astatine shows up and then disappears as part of that process. They don't use astatine, they use cesium as one of the radioactive elements in the hospital. But you've got the right idea. Yes, you got the right idea, but no, they don't use astatine. Okay, so now we can, let's keep going. We've got oxygen's O2, aluminum is Al. That's it, no charge. It's an atom when it's on its own. And then aluminum oxide we have to build. It's a compound. Let's take a look at the atoms and ions there. Aluminum is Al. What's the charge on aluminum when it's an ion? I see that hand, Severit. Oh no, now you have to commit. You've put the hand up. I asked the question, you went while looking right at me. So what's the charge on aluminum? Find it. It's on the right-hand side, about 3/4 of the way over. +3. Oxygen is O, charge of? You like made eye contact with me and everything. Yes, Brooklyn, it is -2. So when you're building aluminum oxide, what's the formula if aluminum is +3? Yep. They would swap. So you'd have Al2O3. I'm loving the gang signs and the dancing from the back corner. It's fantastic. Now we balance. Drop the line. Al and O. Al and O. At this stage, you guys have been balanced. I have given you, if you've done the practice I've assigned, you've done enough of these things to start getting comfortable with the process. I gave you a list of tips at the beginning. They are not good 100% of the time. This is one of those times. The first tip I gave you was start left to right, leave oxygen to the end. If you look at this one though, let's count how many we have here. I've got 2 aluminums and 3 oxygens on the left. I've got 1 and 2 on the right. The first thing that should flag for you in this example is what? There's no polyatomic ions. There is something that should jump out of you immediately that goes against the first tip I gave you. How do the oxygens show up? They show up as groups of 3 over here, and they show up as groups of 2 over here. My first tip was start left to right, leave oxygen to the end. If you do that, you're going to balance aluminum, and then you're going to immediately go ahead and realize that the oxygens aren't going to work, and now you've got to double stuff. If you look at the big picture and say, well, okay, if you recognize that the oxygens are going to give you a problem, the first thing you should do in this question is deal with that. How do we deal with the oxygen problem? Evelyn. You betcha. And in this case, this is one of the rare examples where oxygen first is the right call. So as Evelyn said, because you're going to get groups of 3 oxygens coming from this compound and groups of 2 oxygens coming from this compound and only this compound, the easiest way to deal with this is to recognize that 3 and 2 both go into 6. So I need to toss a 2 out here to give me 6 oxygens, a 3 out here to give me 6 oxygens, and putting the 2 out here is going to give me 4 aluminums coming along for the ride. So then the only thing I have to do to balance this thing is to do what? Put a 4 in front of the Al, and now we're balanced. And you're done. So those are the 2 examples I'm going to do for you. The next 50 or so minutes is for you guys to play with the next, so like questions 1 through 5 and 7 through 9 on this page. I also want you to do questions 1 through 8 on the next page. I do want you to word equation, skeleton equation, and because you've got the time, balance them as well. This is your task. Work until I tell you to stop. I will keep an eye on the clock. I'll let you know when to pack up a little early. If you would like, the mini whiteboards are over here in the white box on the table. If you'd like the big whiteboards, you can move to those. If you'd like to go pencil on paper, like an old school individual, extra paper is by the printer. Do not cram your work into this almost no page unless you really think you have no work to show. Even then, don't do it that way. Show me, do the work either on paper or on whiteboards. That is your task. I will be in and out of the room, back and forth between here and the lab, bringing stuff over. If you have questions, grab me while I'm here. Work with your peers. You may use the washroom, so may you. On your market, say giver. Regina, you got to wait until either Massey or Evelyn comes back. Sounds good. On your market, say go.